Welcome to 3.8, derivatives of trig functions. So in 3.8, we're going to be taking the derivative of trig functions, but more importantly, the inverses of the trig functions. So I'm going to do a little bit of an intro and kind of bring you up to speed with the knowledge that you should have by now. And the first thing I want you to remember is the inverse of a function f of x equals y is found simply by reversing or swapping the x and y values in the function. So if my function is defined as the points 1, 2, 3, 4, 5, 6, the inverse function would be 2, 1, 4, 3, 6, 5. And I want to show you guys exactly what I'm talking about. So here's my function. It's just a list of 3 points, 1, 2, 3, 4, and 5, 6. And so the inverse then would be swapping the x and the y values. So 2, 1, 4, 3, and 6, 5. So this does not necessarily always happen perfectly like this where they're parallel, but you basically just swap the x and the y values. When we solved equations with inverse functions, we would swap the x and the y terms and then resolve for y. It's the same idea. You just swap them. Okay? So, moving on to the theorem of derivatives of inverse functions. So the theorem says if f is differentiable at every point of an interval I and df dx, so the derivative of f with respect to x is never 0, then f has an inverse, and f inverse is differentiable at every point on the interval f of I. F of I simply means that for every point f exists on the interval I. The interval does not need to be negative infinity to infinity. We're definitely going to later restrict the interval to make it differentiable. And now we're going to talk about this theorem a little bit. So what this means is that if f is differentiable on every point and d of f of d of x, so the derivative of f with respect to x is never 0, then and only then is the inverse differentiable. So we need to both be, the function needs to be differentiable and the derivative can never equal 0. So let's talk about why the derivative can never equal 0 now. Well, there's 3 main reasons. 1, a function has an inverse if and only if it's 1 to 1, and we'll talk about what that means in a second. A 1 to 1 function is always increasing or always decreasing. It's never sometimes increasing and sometimes decreasing. It's always one or the other. And again, I'll show you why in a second. And if the derivative equals 0, then that means there exists a horizontal tangent, and therefore the function is not increasing or decreasing at that point. And that breaks the rules. So let me show you what I'm talking about, this 1 to 1 nonsense. So first I'm going to bring up a function that is not 1 to 1. Y equals x squared. And your question is, but Mr. Cooper, what makes it 1 to 1 or what makes it not 1 to 1? Well, I'm just going to pick any point A to put on this graph right here. And A is represented by this value up top right here that I'm sliding around. And let me just zoom out a little bit so we can see a little more clearly what's going on. So you can see as I move A, it moves. And if this input was the only one that gave me this output, we'd be 1 to 1. But unfortunately, I have 2 inputs that give me the same output. Right? You can see right here that there are 2 numbers that will give me the same output. And you can see right here I can connect them with a line. So this makes this function not 1 to 1. Also, you'll notice that at this point right here, when a equals 0, there is a horizontal tangent. Right? There's a horizontal tangent right here. And what that means is that this function is decreasing and then increasing. So this is an example of a function that's not one-to-one. Another example of a function that's not one-to-one is sine of x. So here's sine of x. And this one's not one-to-one. Because look, I have 2 points on the graph. Whoa. I have 2 points on the graph that when I move A, give me the same output. So sine of x is also not one-to-one. An example of a function that is one-to-one, however, is x cubed. Because any point gives me 1 and exactly 1 output. And there's no input, there's no 2 inputs that'll give me the same output. Okay. So you also need to recall, if f and g are inverses, then f of g of x is equal to g of f of x, which is equal to x. Another way we write this is f of g of x is equal to g of f of x, which is equal to x. And this is only unique if they are in fact inverses. Okay. If any of this is confusing, you need to go back and do a refresher course on inverse functions. Alright, so the actual problem we're going to work on today is determining the derivative of sine inverse of x. So the first thing that should be going off in your brain is you should be going, wait, you just told me that we have a huge problem here. What do you think the problem is? The problem is that sine inverse of x is not one-to-one. Right? In order to have an inverse, you have to be one-to-one, but we just saw that the inverse, or that sine of x, is not one-to-one. So this is a huge problem. We're going to go about fixing this. So let's go ahead and let's look at the graph of sine of x. Let's look at the graph of sine of x. So here's our old friendly sine of x. It's nice. And I'm going to put a point AF of A on it, so as I move this, you can see it move. Now the reason that this does not have an inverse, and I'll show you, is if I graph the inverse and play this, you can see that so far we're good, but right now we're no longer a function. And I'm not talking about sine of x. I'm talking about the inverse. Right? There are 2 points on this graph, one input that'll give me 2 different outputs. If you look at this input right here, I get an output of this value, and this value, and so on. So this is not even a function. So we have to think how can we restrict the domain so that this will be a function? Well, I can't restrict it from 0 to pi because then I go like this. So what we need to do is we're going to restrict the domain from negative pi over 2 to pi over 2. So if I restrict sine like this, I'm only using this little piece of sine from negative pi over 2 to pi over 2, right here, then in fact the inverse does exist. And this is the inverse. Here's the original sine function, and here is the inverse. So we end up getting the inverse sine exist from negative pi over 2 to pi over 2, and that's something we should remember from pre-calc. So again, we're going to restrict the domain. This is how we go about fixing our problem. we restrict the domain of sine of x to negative pi over 2 to pi over 2. And this fixes it. Okay, so if I were to draw that on a graph, it would look something like this. And again, I'm drawing sine of x, not sine inverse. It would look something like that. Okay, so this is our new function that we're working with. So we go ahead and we made our interval negative pi over 2 to pi over 2. This is the interval I. This is the interval we're going to be working with. Alright, so the actual problem is we're going to be taking the derivative. So let's go ahead and let's do that. Let's take the derivative. Well, step 1. Step 1. We're going to rewrite the problem. Now, this is where a lot of students make a mistake. They go, oh, no problem. I'll just use the power rule and do the thing. This is sine inverse, not sine to the negative 1 power. They're two completely different things, and it is very, very confusing. So what we're going to do here is take sine of both sides. So we get sine of y is equal to sine inverse of x. The reason we do this is this is how you get rid of sine inverse. You take the sine of both sides. So we're left with sine of y is equal to, and sine inverse cancel each other out. So sine of y is equal to x. So the next step now is to go ahead and take the derivatives. So we're going to take the derivative of both sides. So using implicit differentiation, we get the derivative of sine of y is cosine of y times dy dx, which is equal to 1. So we want to get dy dx all by itself, so we're going to divide both sides by cosine of y. And we get dy dx is equal to 1 divided by cosine of y. Okay, now here becomes a question. Can dy dx be the derivative? And what I mean by that, does cosine of y exist in the new domain that we created? Well, I'm going to pull up a graph of cosine of x. So right here, this is cosine of x on the interval negative pi over 2 to pi over 2. So let's look at the section that we're looking at, where we're looking from negative pi over 2 to pi over 2. So look at that. Cosine does exist from negative pi over 2 to pi over 2. So we're okay. So the original function existed and the derivative exists. All right, now for step 2. So that was step 1. We got dy dx. But the problem is we want it in terms of x, not y. And as you can see right here, it's in terms of y. So we need to figure out how to get rid of that. So here is step 2. This is a little unintuitive, but that's why we're doing it together. We need to find something that's going to relate cosine and sine. Because keep in mind in the back of your head that sine of y is equal to x. That's from almost the beginning of the problem. So what we do is we go sine squared of y plus cosine squared of y equals 1. This is that Pythagorean identity. This is something you need to remember from pre-calc. So our goal is to get rid of this cosine of y right here. So we want to get this cosine of y all by itself. So I'm going to subtract over the sine squared, and you get 1 minus sine squared y. And then to get rid of the square, I take the square root of both sides. So we get cosine of y is equal to the square root of 1 minus sine squared of y. Now I know what you're thinking. I need a plus or minus. It's okay. Because we're dealing with inverse functions, we're only going to look at the positive square root value. Because otherwise we get a plus and a minus, and then one input will give us two outputs, and that's not good. So we have cosine of y is equal to the square root of 1 minus sine of y squared. Now remember, sine of y equaled x. So we get cosine of y is equal to the square root of 1 minus x squared. We are so close to our answer. What we don't want just cosine of y. We want 1 divided by cosine of y. So 1 divided by cosine of y is equal to 1 divided by the square root of 1 minus x squared. Now the question is, do I want cosine of y? No, I don't. 1 over cosine of y, this entire piece right here, is equivalent to writing d dx sine inverse of x. Remember, 1 over cosine of y was the derivative when we did the derivative of sine inverse. So that means this is equal to 1 over the square root of 1 minus x squared. And there it is, the derivative of sine inverse.